All right. Today we're going to talk about the Moivre's, I can't say his name, theorem and the nth roots. Okay, so we're going to be talking about complex numbers. It says, one of the new frontiers of mathematics suggests that there is an underlying order in things that appear to be random, such as the hiss and crackle of background noises as you tune a radio. Irregularities in the heartbeat, some of them severe enough to cause a heart attack, or irregularities in our sleeping patterns, such as insomnia, are examples of chaotic behavior. Chaos in the mathematical sense does not mean a complete lack of form or arrangement. In mathematics, chaos is used to describe something that appears to be random but is not actually random. The patterns of chaos appear in images like the one shown here, called the Mandelbrot set. Magnified portions of this image yield repetitions of the original structure as well as new and unexpected patterns. The Mandelbrot set transforms the hidden structure of chaotic events into a source of wonder and inspiration. So even though this is supposedly chaotic, you can see some patterns. Okay, this one looks like some sort of a spirally thing. All right, you got some repetition going on down here. You got like a black hole here. Maybe that's where black holes come from. I don't know. All right. Anyway, it's chaos theory. The Mandelbrot set is made possible by opening up graphing to include complex numbers in the form a plus bi, where we know I is equal to the square root of -1. In this section, you're going to learn how to graph complex numbers and write them in terms of trigonometric functions. All right. So the complex plane. We know that a real number can be represented as a point on the number line. By contrast, a complex number z equals a plus bi is represented as a point, AB, in a coordinate plane, as shown in figure 6.38. The horizontal axis is called the real axis. It's what we normally call the x-axis. But when you're talking about in a complex plane, that's your x-axis is your real axis. And the vertical axis, which is what we normally call the y-axis, now becomes the imaginary axis. The coordinate system is called the complex plane. Okay, so we've talked about lots of planes. We have the rectangular plane, which is an x and y. We have the polar plane. We have the parametric plane. And now we're talking about the complex plane. Every complex number corresponds to a point in the complex plane, and every point in the complex plane corresponds to a complex number. When we represent a complex number as a point in the complex plane, we say that we are plotting the complex number. And all you do is, if I gave you z equals 3 plus 2i, this means your x-coordinate is 3, and this means your y-coordinate, I'll put those in quotes, your real coordinate would be 3 this way, and your imaginary would be 2 up. That would be the plot of 3 plus 2i. Okay? So now it says plot u, which is 1 plus 3i, so that would be 1 to the right and 3i up. There's 1 plus 3i. And v, they want me to plot as 2 minus i, so that would be 2 right, -1 down. And that would be the point to -i, which is -1. -i, sorry. 2 minus i. Alright, so then they want me to do u plus v. Well, if u is 1 plus 3i and v is 2 minus i, then u plus v is 3 plus 2i. So if I plot that, 1, 2, 3, 2 up, there's 3 plus 2i. Now, it says these 3 points in the origin determine a quadrilateral. Is it a parallelogram? What do I mean it makes a quadrilateral? Let's see. Connect there. Connect there. Connect there. I do not see a parallelogram, do you? Oh, wait a minute. This kind of looks like vectors. And if I do that with that one, and I do that with that one, well, golly, there we go, a quadrilateral right there. Doesn't that look familiar to us? Yes, it should remind you of vectors. And so what we have just discovered is that it shows how the complex plane representation of complex number addition is virtually the same as the Cartesian plane representation of vector addition. If I took the red and added it to the blue, I get the green. Remember, we did that a bazillion times. Okay? So another similarity between complex numbers and two-dimensional vectors is the definition of absolute value. And what they're getting at here is, it says, recall that the absolute value of a real number is the distance from zero on a number line. The absolute value of a complex number, z equals a plus bi, which again looks like we're taking the magnitude. Okay, it's the distance from the origin. It's the distance from the origin to the point z. So again, if I have this complex number, which would be a units to the right and b units up, when you're finding the magnitude of that, you're finding that distance. So this becomes the magnitude of that complex number. And we do it just like we did the magnitude of any vector. It's the square root of a squared plus b squared. All right? So it says, determine the absolute value of each of the following complex numbers. We don't even need to graph it. I'm going to just to show you, but you don't have to graph to figure this out. To get the absolute value of z, you take the square root of 3 squared plus 4 squared, which is the square root of 25, which is just 5. Now watch, if I plot that, 3, 4i, if we looked at it like it was a vector, this is 3, this is 4, and this is 5. So you found the magnitude of z, the distance from 0 to that point, which is the definition of absolute value, is 5. So if I do b, the absolute value of z is going to be the square root of negative 1 squared plus negative 2 squared, which is the square root of 5. If I plot that, negative 1, negative 2i, and connect, that distance is the square root of 5, which makes sense. The square root of 5 is, I don't know, 2 something. And it's a lot shorter than the one that has a distance of 5. Okay? Alright, so now how are we going to go to a polar form of a complex number? Well, they're going to go through the proof of it for you. Okay? It says a complex number in the form z equals a plus bi is said to be in rectangular form. Suppose that its absolute value is r. We let theta be an angle in standard position whose terminal side passes through the point AB. So if you look at my little diagram, they did this, and they're just showing you how this came to be. Okay? And what they're saying is, if I looked at right here, and I labeled my triangle, then cosine of theta would be a over r, adjacent over hypotenuse. Sine would be opposite over hypotenuse, b over r, and tangent would be b over a. So therefore, we can say, if I got a alone, that a equals r cosine theta, b equals r sine theta, and tan stays the same. By substituting these expressions for a and b into my complex form, we can write the complex form as z, and I replace that with a plus bi. You replace a with r cosine theta, you replace b with r sine theta, and then all they did was factor out the r from both of these, and they come up with this is the polar form of a complex number. You don't have to know this. This is just the proof of why that works. There's my formula to change a complex number into polar form. Alright? And please remember, okay, and so some language here. We have polar form of a complex number. To go from standard, from complex to polar, you simply figure out r, figure out theta, plug them in, and you're done. Well, how are you going to figure out r? Same way we always have, square root of a squared plus b squared. And how are you going to figure out theta? Tan theta equals b over a. Now, some language. We call that value of r the modulus of the complex number. And the angle theta is called the argument of the complex number. And then please remember, you're going to be finding that arctan, so you've got to remember your calculator tricks. Your calculator is going to give you the wrong answer, possibly. Alright, so that's why we've got to plot these points and make sure that your answer on the calculator is in the right quadrant. Alright, so it says plot -2 minus 2i in the complex plane and then write z in polar form. So if I plot this, -2, -2i, which tells me I'm in quadrant 3. So I need to remember to do this when I do my arctan. Alright, so I need r and I need theta in order to write this. This is my end goal. Alright, so in order to write it like that, I need my r and I need my theta. So to find r, this a is -2 and b is -2. So r is the square root of -2 squared plus -2 squared, which is the square root of 8, which simplifies to 2 square roots of 2. Okay, there's my r. To find my theta, I'm going to use tan theta equals b over a. So tan theta equals -2 over -2. So tan theta equals 1. Now, you're going to have to be careful here. When you do this in this calculator and they want their answer in radians, remember your calculator is going to give you a stupid decimal. So what I do is I go ahead and I put my calculator in degrees and I arctan, and that's going to tell me that theta equals 45 degrees. So if Math Excel is working in radians, I do it in degrees and then I switch it to radians. So theta equals pi over 4. However, I'm in quadrant 3. Pi over 4 is up here in quadrant 1, so I need to be down here in quadrant 3. So if your calculator, whatever calculator answer you get, since my point is in quadrant 3, I'm going to add 180 or pi to my theta, which that would be theta equals pi over 4 plus 4 pi over 4, which gives me theta equals 5 pi over 4. So now that I have r and I have theta, I can write my polar form, which is r cosine theta plus I sine theta. So z equals 2 square roots of 2 cosine 5 pi over 4 plus I sine 5 pi over 4. And that, my friends, is this in polar form. Okay? And you can work this in decimals, you can work this in degrees, it does not matter. Like I said, I'm pretty sure Math Excel is going to want you in radians. And if you type this in with your mode in radians, it's going to give you the decimal equivalent of pi over 4, which we don't really recognize very easily. So I do the whole calculator thing. If we do the next one, I can tell they want, on the last one I really didn't know if they wanted degrees or radians because it didn't give me any restrictions. But on this one, because they're saying theta is between 0 and 2 pi, I know for sure they want this in radians. So, again, I need, I gotta plot it. So 1 right and negative square root of 3 down, which is a little more than 1.5 something. So we're in quadrant 4. Alright, so to get my r, I'm going to take the square root of 1 squared plus a negative square root of 3 squared, which gives me the square root of, this is going to be 1 plus 3, which is going to be 4, so my r equals 2. To get my theta, I'm going to say tan theta equals b, which is a negative square root of 3, over a, which is 1. So tan theta equals a negative square root of 3. You could also just use your unit circle to figure this out too, but calculator is easier. If I arctan this in degree mode, I get theta equals negative 60 degrees, which is a negative pi over 3. But I'm in quadrant, my point's in quadrant 4, which so is this, but it's got the wrong sign, so I'm going to add 360 to it, and radians would be 2 pi. So that's going to give me negative pi over 3 plus 6 pi over 3, which gives me theta equals 5 pi over 3. So now that I know that, I can say my polar form is 2 times cosine 5 pi over 3 plus I sine of 5 pi over 3. There you go. Okay. Alright, so let's try another one here. Again, we're between 0 and 2 pi, so they want radians. So if I plot that, -3, -4i, we're in quadrant 3. So watch that calculator answer. So I got to find r, and that's going to be the square root of -3 squared plus -4 squared. So that gives me the square root of 25, which gives me 5. To find theta, I'm going to say tan theta equals b over a. So tan theta equals 4/3. Now, I know that there's nothing in the unit circle that does that. So now I'm just going to go decimal, and since they want radians, I'm going to put my mode back in radian mode. And I'm going to arctan. And I get theta equals 0.9273. But for my calculator answer, I need to add 180 to that, which in radians would be adding pi to that. So theta equals 4.07 radians. And so my polar form would be z equals 5 cosine 4.07 plus I sine 4.07. And that would be my polar form. Okay, now how do we go backwards? What if they give me a polar form and they want me to go back to rectangular form, meaning they want me to rewrite it as a plus bi? Well, this is simpler, because all you do is replace this with their exact values and simplify. So this would be 2. Cosine of 60 degrees would be 1/2. Plus I sine 60 degrees would be the square root of 3 over 2. So if I distribute that, I get 2 over 2 plus I 2 square roots of 3 over 2. That gives me 1 plus I square roots of 3. Okie dokie. Alright, on this one, I'm going to have 5/2 cosine of 150. There's 150. Cosine is x, is 1/2. I mean, x is negative square roots of 3 over 2. Plus I times sine 150 is 1/2. So this is going to be a negative 5 square roots of 3 over 4 plus 5 over 4 I, and I'm done. Okay. Alright, you try this one, hit pause, come back when you're ready. And hopefully you got one. So I plot my point, -5. 5 square roots of 3 would be, I don't know, 6 something. Somewhere around there. My point is we are in quadrant 2. Alright, so my r is going to be the square root of -5 squared plus 5 square roots of 3 squared. That gives me 25 plus 75, which gives me 100, which makes my r 10. So those two are out. And then to get my theta, I'm going to do tan theta equals b over a, which gives me tan theta equals a negative square root of 3. So if I arctan this, I'm going to go back to, I know square root of 3 is in the unit circle, so I'm going to go back to degrees and arctan this, and I get theta equals negative 60 degrees, which in radians is negative pi over 3. But since I was in quadrant 2, I need to add 180, which is pi, to my answer. So that would be negative pi over 3 plus 3 pi over 3, which gives me theta equals 2 pi over 3. So now having that, I can write my polar form, r cosine theta plus I sine theta. Okay. Try this one, hit pause, come back when you're ready. And hopefully you got 3. Alright, this can be written as 0 plus 3i, which would be plotted right here. Okay, so you can actually tell what theta is. Theta is going to be 90 degrees. I mean, I'll do the math, but you can tell what theta is going to be. Alright, first of our r is going to be the square root of 0 squared plus 3 squared, which is the square root of 9, which is 3. To get my theta, I'm going to do tan theta equals b over a, which is undefined. Well, the only place that tangent or theta is undefined with tangent is at 90 or at 270, because that would be dividing by 0. Well, I know I'm up here in this quadrant, so theta has to be 90 degrees. So I got my r, got my theta, so z equals r cosine 90 plus I sine 90. Okie dokie. Alright, write this one back in rectangular form. Hit pause. Come back when you're ready. Oops. Oh, the answer wasn't in there. It's 4. Alright, so what you do is you have 8, and you're going to just change these back to their exact values. Cosine 30 is x, so that's going to be the square root of 3 over 2. Plus I, sine of 30 is y, so that's 1/2. Distribute, I get 8 square roots of 3 over 2, plus I times 8 over 2. That gives me 4 square roots of 3 plus 4i. Okay? Alright, try this one. Hit pause. Come back when you're ready. And hopefully you got 3. So I have the square root of 6. Cosine of 315 degrees is x, which is the square root of 2 over 2, plus I, negative square root of 2 over 2. So on top, I'm going to have the square root of 12 over 2, plus, actually it's going to be minus because of that negative, minus I square roots of 12 over 2. If I simplify that, 12 by 2 is 6, by 2 is 3. That's 2 square roots of 3 over 2, minus I, 2 square roots of 3 over 2. The 2's cancel. And I have the square root of 3 minus I, square roots of 3. They put the I at the back, same thing. Alright. Products and quotients in polar form. We can actually multiply complex numbers in polar form, and we can actually divide them. Okay, it says the product of two complex numbers. If you're going to multiply two complex numbers, what you do is you multiply their r's, you multiply their moduli, and you add their arguments. Okay, this is the proof of why this works. I'm not going to go through it. You can look through it at your leisure. But again, this is just the proof of why this formula works. We don't have to worry about proving it. We just get to use it. You will have to prove those things in calculus. Alright, so we're going to start with this one. And it says to multiply these two together, we're just going to follow this. So Z1 times Z2 says multiply the r's, the moduli, and you add the thetas. So this is going to be cosine of 50 plus 100 plus I sine 50 plus 100. So that's going to be 4.7 times cosine 150 plus I sine 150. And there you go. You multiply. Okay. Next one. They're going to try and scare us with ugly numbers, but when you multiply multiply your r's, 25 square roots of 2 times 14 times cosine of, we add the thetas, so negative pi over 4 plus pi over 3 plus I sine of negative pi over 4 plus pi over 3. So if I simplify that, this comes out to 350. This is going to be cosine. I need a common denominator, which is going to be 12. So negative 3 pi over 12 plus 4 pi over 12 plus I sine, common denominator again is going to be negative 3 pi over 12 plus 4 pi over 12. So that gives me 350 cosine of pi over 12 plus I sine pi over 12. Alright, and there is the product of those two. Alright, you try one, hit pause, come back when you're ready. And hopefully you got one. Alright, so if I do z1 times z2, I take 9 times 3 times cosine of 3 pi over 4 plus 5 pi over 3 plus I sine 3 pi over 4 plus 5 pi over 3. Alright, we need a common denominator. That's going to be 27. Cosine is going to be 12 again, so this is going to be 9 pi over 12 plus 20 pi over 12 plus I sine 9 pi over 12 plus 20 pi over 12. That gives me 27 cosine 29/12 pi plus I sine 29 pi over 12. Okay, that is multiplication. Now we get to divide. Well, guess what? If when we added, or when we multiplied the arguments and we added the thetas, when we divide, we're going to divide the r's and subtract the thetas. We're going to divide the moduli and subtract the arguments. And we didn't, if you want to see the proof of why the quotient works, you can find that in the appendix, or they're going to ask you to prove it yourself in 110. Alright, so for this one, they want me to divide those two. So to do z1 divided by z2, I take the r's and divide them. And then I'm going to have cosine of subtract the theta. So 3 pi over 4 minus pi over 4 plus I sine of 3 pi over 4 minus pi over 4. So that gives me 3 cosine of 2 pi over 4 plus I sine 2 pi over 4. I can reduce those, which gives me 3 times cosine of pi over 2 plus I sine pi over 2. Pretty easy, breezy, lemon peasy. Alright, if we look at this one's in degrees, same rules. z1 divided by z2 is going to be the quotient of the arguments times cosine subtract the thetas, 135 minus 300 plus I sine 135 minus 300. So that gives me the square root of 2 over 3 times cosine of negative 165 plus I sine of negative 165. Okay? Yeah. And they didn't ask that. Oh yeah, they did. They want it in standard form, which means A plus BI. So I actually have to do this. So that's going to give me the square root of 2 over 3 Cosine of negative 165 is negative 0.9659 plus I times sine negative 165 is negative 0.2588. And if I distribute and multiply by the square root of 2 over 3, I get negative 0.46 minus 0.112, not 0.12I. Okay, that would be in standard form, and this would be in polar form. Okay. Alright, you try this one, hit pause, come back when you're ready. This one's kind of a twist. They're kind of making you go backwards. And you should get 3. Okay, I use the definition. Z1 divided by Z2 is R1 divided by R2 cosine of theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So here's my quotient of the R's. So this is going to be 8/5, right? And then this is going to be cosine of theta 1 minus theta 2 is going to be 180 minus 50 plus I sine 180 minus 50, and that gives me 8/5 cosine 130 plus I sine 130. And there's where they got their answer. Alright? So how do you plot complex numbers on the complex plane? Well, this would be your real axis. This would be your imaginary axis. And you point A on the real and BI on the imaginary. How do you write a complex number A plus BI in the form R cosine theta plus I sine theta? You have to find R, which is going to be the square root of A squared plus B squared, and you have to find theta by doing tan theta equals B over A, and then you substitute into the formula. How do you find the absolute value or modulus of a complex number? It's the square root of A squared plus B squared. How do you find the product and the quotient of complex numbers? Well, can you write the product form? Z1 times Z2 is R1 times R2 cosine of theta 1 plus theta 2 plus I sine theta 1 plus theta 2. And quotient is Z over Z2 R1 over R2 cosine of theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Okay, and we will answer these other 3 next time. So we are at homework. Happy homeworking, and I will see you next time.